I'll start by giving this quotation by Alan Turing, uh, in which he said that what we want is machines which can learn from experience. Normally, what we have in intelligent systems are offline data set based learning algorithms which do not interact with their environment. So they're actually slave to the data sets available uh, off the shelf. So with that spirit, let's begin with reinforcement learning as to how, first we'll talk about how it's different from machine learning. The first thing to note here is that reinforcement learning algorithms, as I mentioned in the previous slide, take actions and observe, and those actions in effect, they affect the next observation. So in a way, it's a comparison between interaction and perception. Most of the machine learning algorithms which we are which are available and which most people use are actually focusing on perception, like image captioning or natural language processing. But reinforcement learning is much more concerned with actually taking actions and changing its environment and observing how the environment changes. The second thing is that reinforcement learning algorithms optimize on trajectories of such actions and observations rather than instances. One can think that, sure, recurrent neural networks actually optimize over sequences, but the difference here is that the trajectory optimization is built into the algorithm rather than the architecture itself. So even a feed-forward neural network is able to do trajectory optimization once it's actually learning in the reinforcement learning paradigm. Or instead of having a right answer, as with most of the machine learning algorithms in form of a loss function, our algorithms find the best possible solution with feedback from the world. So there is no right answer, but what we want is the best possible answer that our agent can get when it's interacting with its environment. And last but not least, interactive RL algorithm, which is like the majority of the algorithms are online rather than offline. What this means is that they don't rely on data sets, much like most of the machine learning algorithms, but they actually interact with the environment and gain experience as they learn. Now I'll talk about why of reinforcement learning. I'll talk a bit in more detail about this particular algorithm called the DQN at the end of the slides. But here I'm actually mentioning it because of its performance. So what you see here is that this bracket is the superhuman level performance of this DQN algorithm. Now, it is impossible to achieve a level beyond the dataset without any interaction with the environment. As if for example, you just rely on the dataset and the dataset is actually acquired by humans. So you cannot actually surpass humans in any case. To actually achieve superhuman level accuracy or performance, you need an agent to interact with the environment to find better solutions than the human themselves. And as I work in the robotics domain, so this particular demonstration actually fits well with the theme. This particular demonstration was shown by Mr. Peter Abel at NeurIPS, I think 3 years ago, in which he actually gave this very cool demonstration of a PR1 robot doing these house chores and doing all these fancy things. And the audience was actually dumbfounded, and they were actually quite amazed that this thing has been achieved. But there was a catch. The catch was that the robot was being controlled manually. One would think that this is just a trick, but there is a very, very key takeaway from this demonstration. The key takeaway is that robotics is now a software problem rather than a hardware problem. The hardware is there, but we need to work on software or algorithms to actually make the robot function as we are seeing in this particular video. And this interactive setting of a robot is actually quite ideal when we think about reinforcement learning and how it actually learns from the environment. Now let's talk about Markov decision processes, which is just a fancy word It just states that whatever you see in the environment at any given time is sufficient for you to take any decisions. I'll give a bit more detail as we go along. So in the start, there is an environment and there is an agent. The agent is our reinforcement learning agent or reinforcement learning algorithm. The agent observes the state of the environment and it takes an actions. And with those taken actions, the environment state changes and the agent observes the next state. This is the main framework on which reinforcement learning algorithms are developed and they work. Agent interacting with the environment, observing states as it takes actions. Now to get a bit more comfortable with this concept, let's see a real world example of a squirrel in an obstacle course. All thanks to Mr. Mark Rober. He's a very great YouTuber. In this particular video, what you see is a squirrel doing actions which they not normally do. So there is some sort of a human conditioning going on in this particular demonstration. And we'll actually dissect this particular snippet in form of Markov decision processes. Now, to start, this is our agent, and the rest of the course is our environment. Okay. Now, the obstacle course, we have actually concluded that it's our environment. It produces a state which is being observed by the agent as it sees that it is in a particular position in the obstacle course, and it's seeing that it has some object of interest through it is seeing some object of interest through that hole. So to achieve that object of interest, it puts its head through the hole, and in return it gets some delicious peanut butter, and we get a nice picture, which normally squirrels don't actually are eager to give, or we can't take these pictures in nature. The difference from the Markov decision processes and this particular loop is this motivator called the reward, which is actually the only feedback system which the agent observes from the environment as it takes actions. And this actually governs how the agent's responses change over time to the optimal one. Okay, to put it more formally, in reinforcement learning, an agent is put in an environment where it, at time t, it observes a state S sub t and takes an action A sub t to get a reward R sub t and transitions to the next state R sub t plus 1. The key difference here is this reward, which was absent in the vanilla Markov decision processes. This entire loop is what every reinforcement learning algorithm actually tries to do. It actually tries to optimize these actions to get the maximum rewards possible. But I'll define this concretely when we talk about the objective. So the transition from this S sub t to S sub t plus 1 is governed by something called a transition probability. And this probability actually represents the environment itself. For example, if you take an action in a particular state, the environment responds by shifting you to a next state and giving a reward. So this entire probability is actually inside of this green box here. So an MDP is, or what we call Markov decision processes for short, it represents a trajectory of states, actions, and rewards. What we saw earlier was just one instance, but what you can see here is that, at state S sub 0, A sub 0, you take A sub 0, get R sub 0, and it continues till this terminal state S sub capital T. And this terminal state actually ends the interaction of the agent with the environment. Now, the objective of reinforcement learning is to take optimal actions to accumulate optimal transition rewards RT. Optimal transition reward meaning that it gets as much reward as it possibly can juice out of the environment by taking optimal actions. The accumulated rewards are collectively called the return. I'll talk about this word a bit below. And the return is given by this simple equation. It's just the accumulation of all the rewards from a state S sub t till the end terminal state R sub capital T, where this capital T, as we saw above, is the end. It represents the end of an episode of interaction. And the word return is used here because the environment actually returns the rewards. This word is taken from the gambling perspective, but it actually works quite well as if you think about it a little. The environment actually returns the reward to the agent. Okay, now before diving into what goes on inside an agent, let's just look at some examples from industrial control, robotics, and games to set the tone right in terms of what type of problems can be solved by reinforcement learning. Now, industry control, I'll give the example of a data center cooling and industrial control system, which was deployed by Google's own DeepMind branch at its data center at Bluff, Iowa. The environment here consists of all the physical sensors in the data center, which actually measure the state of the environment. And the agent are the neural networks, or the AI, if you call it in layman's term, that actually regulates the energy consumption and finds optimal actions to take. If you go step by step, in the start, every 5 minutes, a cloud-based AI pulls a snapshot of the data center cooling system as represented by those thousands of physical sensors. Then this information is fed into the deep neural networks, which is actually, in our case, the agent, which predicts the future energy efficiency and the temperature based on the proposed actions. The AI then selects the actions that satisfy the safety constraints and minimize future energy consumption, meaning that it optimizes its actions as in response to the state it has observed. These optimized actions are then fed back to the system data center, where the local system verifies them against its own safety constraints. So there is a double check, and then these actions are implemented. What you see here is a feedback loop, and this feedback loop is the same as what we saw earlier. There is an environment, the agent observes the state of the environment, the agent does some actions, and the state of the environment changes accordingly. Now, in games, the first game which we should talk about is the game of Go, which actually was the first time publicly reinforcement learning's capabilities were highlighted. The key thing here is to note here is that this game of Go looks very simple in terms of the moves which we see here, but the number of states, the possible states, are more than the atoms in the universe. So just going brute force and trying to find the best possible move at a particular time step is totally out of the question. So this was a very big feat that an algorithm was able to optimize for a particular problem which was computationally intractable. And this particular instance is of the move 37, which was actually the very surprising move from DeepMind's AlphaGo, which actually took Lisa Dole, the world champion, by surprise. Here you see that the agent is actually the computer screen that is actually taking the actions, and the environment is the board itself. Now moving on to computer games, which are a little bit more interesting. Here the environment is the game screen, and the agent is the player. Now you see the difference here is that the agent is not supplied with the position of this, for example, this slider or this slider. It's actually just processing the pixels directly and is able to optimize actions based on that pixels it's just seeing. So this actually encompasses the main strength of reinforcement learning algorithms in comparison to other control related or AI-based systems. Expanding a bit more on the games, computer game side, Dota 2 is a bit more complicated game, quite complicated game. But the main thing here is that there are 5 agents working in cooperation rather than 1 agent. What this means is that it's a multi-agent problem, and a reinforcement learning is able to optimize with this type of setting as well. Now moving on to the physical realm of robotics, these 3 examples are all using pixels for as the state input. So there is no dynamics being told to the algorithm. It does not know how this genes or how this block or how this particular joint or how these balls are actually behave in response to their actions. What they do is they just learn by trial and error or by interaction, and just try to optimize the motion of the motors to do the task which is actually being asked them to do, for them to do. The drone setting is a bit more similar. It's a bit more complicated. Why? Because the controller, the agent itself is a bit more complicated to learn. But in this example also, the agent is actually just being fed the visual information, and it actually is optimizing for the best trajectories just by interacting with the environment. In mobile robotics domain, the autonomous navigation systems are of particular interest because they are computationally very, very heavy for robots to, for remote systems to be working upon, because these are computationally very intensive. But with reinforcement learning, you can actually use reinforcement learning algorithms to work on end-to-end learning systems, so that the learning-based systems are actually compressing all the processes into a series of matrix multiplications, which actually smooth out or make things easier. Here the agent is the robot, and the environment is being presented by the visual state and the LiDAR input. And no talk of AI is complete without talking about humanoids. This is a very cool paper by researchers at Seoul National University, where they actually made a simulation of a human muscular system with 22 joints with their angles and 346 muscle actuators. If you think about first principle approaches of dynamics modeling, this is a very, very difficult problem to model by hand. But reinforcement learning algorithms are able to find the optimal solutions for these complicated problems as well. Now that we have understood what type of problems can be solved by reinforcement learning algorithms, let's now understand how an agent learns itself. Now, as defined earlier, I talked about the return, which is actually the accumulated reward, which actually is of interest to us as we want to optimize the trajectory. But this is for a particular trajectory. And the world is quite uncertain and there are a lot of possibilities. So we need to take all possibilities into consideration. And with that, we need to actually focus on expectation rather than instances. Now, an expected value is the sum of all possible values times their probabilities for a particular variable. For example, consider the fact that by taking an action AT in a state S sub t, the agent is likely to land in one of 4 states. Let's say by taking some action, it actually has some with probability P1, P2, P3, and P4. It has it is probable that it can land in one of these 4 states. Now, to encompass all of these uncertainties into a single value, what we do is we multiply these rewards by their probabilities and sum them up, making outputting an expected value of a state transition return. For deterministic environments, which we know about, for example, we know in some case that taking an action would lead to a particular state and no other state, then the probability is reduced to binary probabilities, meaning that all of them would be 0 except one would be 1. So this would be the reward which we will be getting. The others are out of the question. But this is for simple problems. In a more generic setting, we should take care of all the possible states that can be achieved by an action. Now, another problem that we have to talk about is what if this terminal t goes to infinity? To bound an infinite sum, then we need to use a discount value to penalize rewards of future states in such a way that, for instance, if we are at the start of the environment interaction, the initial reward, state transition reward, is taken as is, and the future rewards are discounted by this value which is between 0 and 1, so that these values grow smaller and smaller and smaller and smaller, and it is mathematically proven that this sum is always bounded to a finite value and does not blow up. Here the capital R is for the expected value, as we talked about earlier. Okay, now that all is fine, but how do we actually represent an agent? Now the agent is represented by 2 things: policies, which actually is responsible, or which actually is looked upon by the agent to take actions, and value function, which I'll describe later. For context, a policy is different from a strategy in the sense that policy depends on changes in the environment, while the strategy is independent of the environment. So in this case, it is easier to understand that a policy is thus a mapping from states which are being visited by the agent, as we saw earlier, to a distribution over actions, meaning that a policy pi is actually something that actually outputs a distribution over actions when the agent observes a particular state. The thing to notice here is that policy is reciprocating the environment, and intuitively a policy is actually a probability distribution over actions, as I mentioned earlier. But how does an agent follow a policy? By visiting states that have the most value. What it means is that we need to associate a value function with the environment, or values with particular states. The question asked by this value function, or the 2 types of value functions we'll talk about, is how good is it for the agent to be in a given state? There are 2 types of value functions, each dealing with one aspect, the state and the action of interaction with the environment. The one is state value function, which just focuses on the states. And the second is the action value function, or the Q function, which focuses on the actions taken in a particular state. Now, we want to optimize for the expected return. That is the objective of reinforcement learning, right? So it makes sense to define the value functions in terms of these expected returns. So the value is actually, the focus of values is actually maximizing the expected return. Now, the state value function gives the value of being in a state S following a policy pi. At any time step t, the value of a state S is given by the expected return, as I told in the previous slide, following that policy pi. You should not be scared of this particular instance. This is just a numerical representation of the expectation we just talked about. And this is just a condensed representation of that discounted sum which we talked about earlier. This expectation, however, is not due to the transition probabilities. It is due to the policy, because a policy itself is actually a probability distribution over actions. Okay, so the second type of action value function is the action value function, which gives the value of taking an action while being in a state, while and then following a policy pi. At any time step, the value of an action in a state is given by the sum of the immediate reward, which is definite because taking a particular action would lead to a particular reward, and afterwards following the expected return as per the policy. So what you can see is, like, if this is of a state S sub t, then this is the value function or the state value function for the next state. So the only difference here is that we are actually focusing on a particular reward rather than the expectation over rewards for the first step we are taking. The value of the Q function, which is called the Q value, is giving us the quality of taking an action. So the Q actually comes from quality. Okay, so how do RL agents learn? The value functions give us the measure to compare states and actions, as we saw, in terms of the expected return. As we defined earlier, the objective of an RL agent is to maximize the expected return. So how do we select optimal actions? By following the optimal policies. But the problem is that value functions actually are dictating the policy, and the policy is dictating the value function. And this egg and chicken and egg problem is actually the main reason why we do not go for analytical solutions and we have to go with iterative optimization solutions, because we do not know which is the cause and which is the effect. They both depend on one another in one way or the other. So the first thing we should do is to have a concept of comparison between two policies. And the policy comparison stated as a policy pi is considered to be better than a policy pi star or pi prime if for all the states the expected return of the pi is greater than or equal to pi prime. What it means is that every value, state value or action value in the state value function or the action value function should be better or at least equal to all the other possible to the other policy, for instance. Now, the optimal policy would be the best among all the policies, right? So the comparison would be going on with all other policies possible. A policy that is better than or at least same as all other policies with respect to the expected return is an optimal policy. It's a very straightforward definition that you need to optimize the policy to get the maximum expected return. So the policy that actually gives you that is the optimal policy. In a more mathematical sense, what we see here is that this policy pi star is better than all other policies if the state value function for this particular policy is better or the maximum achievable in all the policies. And this holds true. It's mathematically proven, and this holds true. Optimal state value function, as defined in the previous slide, is the function value function associated with the optimal policy. And this gives us the largest expected return achievable by any policy for each state. Similarly, optimal action value function is the action value function associated with the optimal policy, and it gives the largest expected return achievable by any policy for each state action pair. The key thing here is that the Q function is actually a decomposition, or I should say a more detailed view of the environment, because you're decomposing a state into the different actions which can be taken in those states. Maximizing over those actions is actually equal to choosing the maximum value for each state. Okay, now we know how to classify an optimal policy, but defining an explicit rule to find the optimal value optimal policy is the way to go. So the definitions of optimal value functions are recursive. What I mean by this is that the next state value function is embedded in the present state value function, meaning that the optimal value for this particular state with a particular action contains within it the optimal value for the next state and some next action. This is the strength of reinforcement learning algorithms, which is the ability to define optimal trajectories or sequences with single values. So the recursive optimality is known as the Bellman optimality. which is just a restatement of what we saw earlier, is that this is the action which the reward which we get by taking this action. But afterwards, what we want is to go for the maximum Q value achievable for the next state. And this cycle repeats. In the next state, t+1 goes here, t+2 comes here, and on and on and on and on until we reach the capital T or infinity or whatever the problem we are dealing with. So this recursive nature is actually responsible for us to find optimal trajectories by focusing on single scalar values. Okay, now I'll talk about an algorithm and its implementation, which is called the Q-learning algorithm. I chose this algorithm because of two things. One, it's easier to understand in comparison to other algorithms, and two, it conveniently extends to the deep learning paradigm. So I'll expand on this particular algorithm in the deep learning paradigm as well. Okay, it's a technique to learn the optimal value in an MDP. And once we have an optimal Q function, we can follow an optimal policy by selecting the actions that give the maximum Q values in each state. And by selecting those actions, we get the optimal policy. But how do we find those optimal Q functions? Well, Q algorithm iteratively updates all the Q values using the Bellman equation, which we saw earlier, until the Q function converges to the optimal Q function, Q star. Okay. Let's look at an example to understand it a bit more concretely. Okay. So this right here is a lizard game. In the lizard game, the lizard wants to eat as many grasshoppers as possible in the least amount of time without stumbling across a bird. The lizard can move left, right, up, or down. So it has 4 actions, and there are actually 9 states: 1, 2, 3, 4, 5, 6, 7, 8, 9. And the states are these individual tiles on the board. Okay. Now, the agent or the lizard gets a reward of +1 if it actually lands on the tile with the grasshopper. It gets a reward for landing in any empty tile -1, and the reward for landing on the tile with 5 grasshoppers is +10 and will end the episode. And similarly, the reward for landing on the tile with the bird, which we don't want, is -10 and will end the episode as well. Okay. At the start of the game, the lizard has no idea of what action to choose, right? What this means mathematically is that the Q values are initialized to 0. Now, what you see here is a Q table associated with the environment we are discussing. These 4 values are actually associated with 4 state action pairs for each particular state. This is the Q value for moving to the right. This is for Q value for moving upwards. This is for left action, and this is for the downward action. Initially, they're all initialized to 0. This is the state. This is called the Q table, which actually encompasses the entire environment and the actions which we can take in that environment. Over time, as the agent plays, the Q values produced for the experienced state action pairs will be used to update the Q table until we find the optimal values. Okay. Now, first we fix the number of episodes because, or we can define a certain criteria of convergence, but most of the time we use fixing the number of episodes of learning. The learning process will take place during these episodes of interaction, and the episodes are defined or are bounded by the lizard at landing on a bird or 5 grasshoppers, or we can actually define a stopping criteria if it doesn't visit these ending states. Okay, now in each episode, the lizard chooses an action based on the current highest Q value in the table for each state. The problem here is the Q values have been initialized to 0. So there is no preference. So in this particular instance, what I need to talk about is the dilemma or the trade-off between exploration and exploitation, which we will be using to actually learn or gather experience and learn at the same time. Now, in exploration, exploitation, the exploration part is the act of exploring the environment to find information about it. And the exploitation is the act of exploiting the information that is already known about the environment to maximize the return, which is what we want. But just exploiting is suboptimal. Like we saw earlier, all the values were initialized to 0, so there is no preference. Whatever you do, you won't be able to find the optimal policy. Okay, so what you see here is that if, for instance, with following suboptimal exploitation, certain loops can be actually occur, certain loops in learning can occur, which actually can bound the agent to visiting states which are actually suboptimal. So we need to explore to find better states. Okay, better states can be found through exploration, as I said earlier, but just exploring is also suboptimal, because if we are not using the information we have gathered about the environment, then we can't transition from state to state in an optimal manner. Hence, there has to be a trade-off between this exploration of finding new information about the environment and exploitation. So how do we implement this strategy? Well, one of the famous strategies which we use in most of the deep learning algorithms, reinforcement algorithms, is epsilon greedy strategy. In epsilon greedy strategy, epsilon is the exploration rate. Epsilon is a value that is initialized to 1, which means 100% exploration strategy, meaning that all the actions that the agent takes is to explore, and it's not following any particular exploitation policy to which it has actually learned. Okay, the epsilon is decayed throughout the learning process, shifting the action control from exploration to find as much information you can about the environment to exploitation as the agent learns and converge to an optimal policy. So if you want to understand how the actions are selected, basically in all of the algorithms which I have actually seen, a randomly generated number is compared, randomly generated number between 0 and 1 is compared with epsilon. And if it is greater than epsilon, then we take an action with respect to our present policy. And if it is less than epsilon, we take a random action. Okay. Now, Lizard will explore in the first episode. It's very intuitive, but I'll explain that, as we saw earlier, at the start, epsilon is 1. So in the first episode, the agent is just taking random actions. With those random actions, it is still updating its Q table, as we'll see later on. So all the actions are actually performed to gather more and more experience about the environment. Suppose the agent moves right and gets a -1 reward. The Melman equation is then used to update the Q value. The problem is that the Bellman equation talks about optimal Q values, but as we'll see in the next slide, this can be exploited to actually learn the Q values themselves. Okay, this is a very dense slide, I understand, but it is a very important one, so I can't skip it. The Bellman equation, as we saw earlier, is actually talking about the optimal Q values by talking about the immediate return and the optimal Q returns afterward. The update rule states that what we do is we nudge the old Q values, in this case zeros, to the new best possible values. Now this maximum is with respect to all the present Q values for the next state. So what this means is that we actually trying to update these Q values as per the maximum reward achievable in that particular instance in our learning process. And when these two values converge, or this update rule reduces to a very small value, this means that we have actually achieved the optimal Q function, because if you plug optimal values, we'll only get optimal values. And this is actually the key ingredient in actually optimizing a Q value function with no information about the optimal Q values. Okay, as the future Q values are still 0, for example, if you're taking a right action, moving to this state, these all Q values are 0, so the maximum value here is 0 as well. So this alpha is the learning rate. In the machine learning community, it's very common. And the gamma is the discount factor, which I described earlier. Setting discount factor to 0.9 as an example and setting the learning rate to -0.5 gives us a new Q value -0.5 in this particular state. And this process actually continues on throughout the learning process. And with this update rule and these values changing over and over again, the algorithm converges when these changes do not have any effect. So these learning rates is -0.5 and the gamma is the discount factor. So what you've just learned is a very, very cool reinforcement learning algorithm in a few slides. Okay. Okay, once the Q function converges to the optimal Q function, updating will have no effect. The optimal policy is thus obtained as described earlier. And if you had difficulty digesting that particular slide, like slide before, you can just see this image and understand. In the start, changing the value function to a better value function enables you to find a better policy. Better policy enables you to find an even better value function. And these two iteratively optimize one another until we reach the optimal values for both. I've taken this snap from the value iteration algorithm, but the idea of Q-learning is also the same. Okay, now we've learned Q-learning. We've learned how a reinforcement learning algorithm works, but it was a very small problem. It was a toy problem. So what if the state space is extremely large and complex? Well, now we move towards deep reinforcement learning, which actually is able to mitigate this shortfall of simple reinforcement learning algorithms. The lizard game had only 4 times 9, 36 state action pairs, so 36 values to optimize. As the Q values are updated iteratively, the number of these iterations are directly proportional to the number of states and the number of actions in the environment. So as the number of states grow to a very large set or possibly continuous value set, then this Q table strategy will not work. If this value goes to a continuous or infinity or a very big sum, then this would be computationally intractable. So what we need, so how can Q-learning, for example, play a game of breakout that we saw earlier from a set of pixels, as I talked about earlier, like this? It is like being played by a Q-learning algorithm, but let's see how. Okay, rather than using a value iteration, which we saw earlier of finding better and better Q values, we use a function approximator to approximate or estimate the entire optimal Q function. Deep neural networks are ideal for approximating high dimensional spaces, so we employ deep neural networks as the Q function approximators, and the algorithm is then called deep Q learning. So the seminal paper of deep Q-learning, which actually handled all the application-related limitations, is a deep Q network, which is actually a very good paper by Vladimir Neh in 2015. And the demonstration I talked about a bit earlier when those superhuman level rates were actually shown to you. DQN was the first major breakthrough in the deep RL domain, which was actually visible to people, and it is one of the highest cited papers in deep reinforcement learning. It uses a deep neural network. It used deep neural networks as the state action function approximator or the Q function approximator, not Q values, the entire Q function. Out of 49 Atari games on which it was tested, it outperformed existing RL methods in 43 games with identical hyperparameters, which was a feat in itself. So the main contributions of DQN are the use of multi-layer convolutional network, so to process the visual input of pixels, utilization of a target Q network. Now this is a bit of an addition which is actually not in the literature of the vanilla reinforcement algorithms. The issue here is that we are actually updating the entire Q function as we are updating the network. So shifting Q function actually shifts all the Q values, and using those Q values as the target, as we saw earlier, is suboptimal and actually can cause optimization and convergence problems. So what we do is we actually have an identical network to the main Q network, which actually stores a previous instance of our main network. And then that previous instance is used as the target Q value, and the stability is achieved in the convergence process. The last thing, the last of the contributions, or the biggest contribution in this particular paper, was the implementation of experience replay. There is a limitation of deep neural networks of converging to suboptimal solutions. To mitigate that, an experience replay was employed, which actually used randomly sampled past experiences to mitigate correlations between consecutive state inputs. So this shuffling actually enabled the deep reinforcement learning algorithm, or the deep neural network, to optimize to optimal Q functions rather than suboptimal Q functions. Okay, now the structure of DQN is as follows. There is a main Q network, which is just a feed-forward neural network. And in the DQN's case, there were 18 actions. So there are 18 values in the output layer. So this is actually the state action pair. For each state, there are 18 actions. Then there is the target Q network, as I talked about on the previous slide, which is actually an identical network with a bit delayed weights, for instance. We input images of the breakout game, for instance. We get the q value, the q function, not the q values, the q function, or the q values for this particular input state, and we compare it with this value, which is actually the same, which is the same as what we discussed in the q learning algorithm. This error is then back propagated, and then afterwards we update the target network after some iterations to store a previous instance. In the paper, I think it was 10,000 iterations. After every 10,000 iterations, the weights of the main queue network were shifted to the target queue network, and then for the next 10,000 iterations, this was locked to those same weights. Okay. Now let's see how a reinforcement learning agent, deep reinforcement learning or deep Q learning agent actually performs over the time. After 16 hours, you can see it actually can play quite well. Well, not in on a superhuman level, as we'll see in a bit in some few seconds. In 34 hours, it's actually able to not lose at all. And let's just keep on rolling. Okay, it's doing well. It's doing well. It's not losing any lives. Okay. Yeah, so this is the tunneling strategy. What it means is that you can actually dig a tunnel and actually push the ball on that particular tunnel so that it actually bounces from these upper walls, and actually you can get more rewards for less number of actions. And this is a strategy that this deep Q learning or DQN actually learned by itself, by experience. This is how superhuman level performance is achieved, by interacting with the environment and seeing how optimally can we select the actions. Okay. Now, as with every field, there are some extensions as well. If the action space is continuous, deep Q learning cannot be applied. Why? Because as you saw, for each state input, we were having a particular number of actions. For action spaces, we employ something which is called policy gradients, which is above, which is doesn't actually meet well with the scope of this course. It's a bit more complicated, but as a suggested starting point, I would suggest you all, if you are interested in continuous action spaces as it is with robotics and motors, to read on this algorithm called reinforce. It's a seminal paper. It's quite interesting, a bit more complicated, but you'll get the hang of it as you now understand how Q learning works. Okay, now with every field, there are some challenges. The first challenge which we actually have to see is, or talk about, is the reward function designing. In the lizard game, I defined the reward functions myself, and in most of the cases, we do that ourselves. And this is a big shortfall or a big limitation of reinforcement algorithm, because if we are trying to make an algorithm which actually goes on and interacts with the world and learns, to guide it every step of the way is not a very ideal solution to unknown environments which we even do not know something about. The other thing to note is sample efficiency. As we saw earlier, gathering experiences is not always the optimal way to interact with the environment, or to put it a bit more concretely, the experiences gained by the agent do not actually process to, or are not utilized to their full potential. The third limitation or the challenge is efficient exploration. The exploration strategy I talked about was a hard-coded strategy, which was actually being controlled by us, and it had no relation with the problem itself. Then there is the safety aspect, because as we saw, reinforcement learning can be applied to control algorithms, and safety critical control systems cannot even, you cannot actually rely on a machine with even 99 or 99.99% accuracy. So mathematical guarantees are required. That is why reinforcement learning, a lot of work is actually being going on to actually mitigate the gap between theoretical control algorithms and these empirical methods of reinforcement learning. Sometimes defining reward functions is not enough. So in this case, for instance, we defined a reward to optimize for the number of points scored, and the agent actually found a loophole in the game and started collecting these points. Now, what we wanted was for it to win the game. By winning the game was actually a bias which we had to encode. So in inducing some sort of a bias of behavior is also something that is being explored in the reinforcement learning domain, because reward functions do not fully capture the essence of the problem most of the time. So with these challenges, I'll wind up my presentation. Whoa, it's almost time. And I thank you all.